Welcome back. This time we're going to talk about understanding and solving the vanishing gradient problem. But before we get started, hit the like button, subscribe, and share this with anyone you know taking the AWS Machine Learning Associate exam. The vanishing gradient problem is a fundamental challenge in training deep neural networks. It particularly affects deep feed-forward networks and recurrent neural networks, directly impacting training stability and convergence in production systems. So, what's the core problem? Neural networks learn through gradient descent, updating weights based on the derivative of the loss function, the gradient. In deep networks, these gradients propagate backward through many layers during training. As they pass through each layer, they can shrink exponentially, especially in early layers. When gradients approach zero, weights stop updating effectively, stalling learning in those layers. This gradient decay accumulates across layers in deep feed-forward networks and across time steps in RNNs. The result is slower training, poor convergence, and suboptimal model performance. Networks might fail to learn complex representations despite having sufficient capacity, wasting compute resources on prolonged training that never converges properly. So, what's the impact on the workflow? This problem undermines deep learning models deployed through Amazon SageMaker, particularly affecting custom model training using TensorFlow or PyTorch containers. Recurrent networks for these time series predictions, or NLP, and deep CNNs for image recognition. In production, models with vanishing gradient issues fail to learn complex representations, requiring excessive compute through prolonged training and produce poor inference results on real-world data. So, what are the solutions? All right. One, better activation functions. ReLU, which you talked about earlier, is rectified linear unit, right? This is the standard activation function in modern deep networks because its gradient is constant, 1 for positive inputs, and avoids the vanishing gradient problem entirely. The formula is simple but effective. TensorFlow, PyTorch, and all major machine learning frameworks in SageMaker support ReLU natively. Variants like leaky ReLU and ELU, which is exponential linear unit, provide additional benefits in specific scenarios. These alternatives address the dying ReLU problem while maintaining gradient flow through the network. Solution 2, specialized architectures. So some architectures are explicitly designed to preserve gradient flow. LSTM, the long short-term memory, these networks control information flow through gates, avoiding vanishing gradients over long sequences in time series and NLP tasks. ResNet, residual network, this introduces shortcut connections that allow gradients to flow directly through layers, making it possible to train networks hundreds of layers deep for image recognition tasks. Both architectures are available as built-in models or through custom scripts in SageMaker training jobs. Finish solution 3, layer-wise training. So, greedy layer-wise training trades shallow network connections first, then freezes those layers and stacks additional depth. While less common in modern production workflows, this approach provides conceptual value for understanding how to manage gradient flow in very deep architectures. Number 4, gradient checking. So gradient checking compares analytical computed gradients to numerically approximated gradients, verifying correctness in custom machine learning code. This debugging technique isn't used in standard SageMaker workflows, but helps validate implementations when building custom training logic. All right. So for LSTM training on sequential data, you'll need to use custom PyTorch or TensorFlow containers, define your architectures, and then ensure you're using the frameworks built in for these implementations to handle gradient flow properly. What are the cost implications here? Vanishing gradient mitigation affects training costs in 2 ways. 1, improper mitigation, like using sigmoid activations at deep layers. This causes slower conversion, longer training times, increasing instance hour charges at your compute. However, architectures like ResNet and LSTM require more powerful compute, typically GPU instances like the ML.P or ML.G types. CPU instances like ML.M cost a lot less, and these are suitable for simple models. GPU instances like the ML.P cost around $3 an hour. So you can train deep models much faster, but the costs are going to increase. Additionally, SageMaker notebooks bill for underlying instances plus the EBS storage. The key is balancing proper architecture choices against training time so that a model that converges in 2 hours on a GPU might never converge on a CPU with poor activation choices. So finding that balance really matters. Anyways, for the exam, when questions arise asking about training instability in deep networks, choosing between activation functions, or selecting architectures for very deep models or long sequences, understanding vanishing gradients to this degree will guide you to the correct answer. Anyways, thank you for joining. Before you go, hit the like button, subscribe, and share this with anyone you know taking the AWS Machine Learning Associate exam. Thank you. Have a good day.